Hi, everybody, and welcome to this new coffee break with Eddyfi. My name is Frederic Reverdy, and today we're going to talk about Phase Coherence Imaging, or PCI. You have my email address in case you have any questions after. So there has been a lot of discussion regarding PCI, so we felt that it would be actually good to present the advantages and the disadvantages of the technique. Contrary to belief, PCI is actually not new. There is prior art. It has been proposed back in 2009 as an alternative method to improve resolution and contrast. I give you here a list of publications, and if you are interested by comparison of TFM and PCI, I think the last three papers are actually pretty interesting. So what's the idea behind PCI? PCI, as the name implies, is based on the phase dispersion or the phase coherence between the different elements of the FMC matrix. The intensity in the PCI image depends on the nature of the indication. When you have omnidirectional sources like a porosity, deep diffraction, or slag, we tend to have pretty high intensity for the PCI because a lot of the pairs in the FMC basically are in phase. At the opposite, when we have reflectors with a strong directional dependence, like a back wall, front surface, delamination, they produce pretty low PCI values. So in theory, PCI should help for the detection of volumetric defects and the identification of crack tips for sizing. So how do we calculate a PCI image? So I'm going to use a full matrix capture for illustration. As we all know by now, the FMC is obtained by firing all the elements one by one and by recording on all the receivers every time. So we have a matrix of n emitters by n receivers. And I'm going to start by re-explaining how do we calculate the TFM. For TFM, we define a region of interest, which is composed of pixels. And let's look at one pixel, that pixel P, for example. So how do we calculate the intensity of the pixel? So what we do is, let's pick one signal. We calculate the time of flight to go from the emitter to the pixel back to the receiver, which corresponds to this time of flight. From this time of flight, we extract the amplitude, and we obtain the amplitude for that particular signal of the FMC. And we do that for all the signals of the FMC, so all the couples, emitter, receivers. And then we sum all the amplitudes, and we obtain the amplitude for that pixel. And then, of course, after we do that for every single pixel of the TFM image, and we obtain here the TFM with a front surface, back wall, and some indications. So for PCI, we need to transform the amplitude versus time into phase versus time. So one way to do that is to divide the signal by the modulus of the Hilbert transform, and then we obtain the phase versus time. So we can see here the indication which corresponds to this one. This indication corresponds to this one, and in between we only have noise. Another way of doing it is to actually calculate the sign of the FMC signals. So instead of calculating the phase, I'm just going to take a 1 when my signal is positive and a -1 when my signal is negative. So that's what I obtain. I can see here my indication, same thing here, and in between I have noise. So every data point in my signal is composed of 1 and -1. So replace every signal of the FMC by this 1 and -1. We obtain the same matrix of n times n phase versus time, and the process after is literally the same as TFM. Extract the signal, we calculate the time of flight to go from the emitter to the pixel back to the receiver. This is the time of flight. We extract the phase, we obtain the phase for that signal. We do that for every single signal. We sum all the phases, and we obtain the phase value for that pixel. And then we do that for every single pixel, and we obtain our PCI image. So if one knows how to calculate the TFM, it is pretty straightforward to actually calculate PCI image. So let's look at some comparisons between TFM and PCI. And to start, I'm going to use a very simple configuration. I just have a mockup with 3 side drilled holes. I'm just going to use a 64 element 5 meg L0 configuration. And I'm going to use the FMC as an acquisition. So here on the TFM side, we have our front surface, our back wall, our 3 holes right here. We can see the amplitude decreasing with depth because we have some attenuation. And if we look on the PCI image, we see that we have disappearance of the front surface and of the back wall. The second thing we notice here is the high value of the PCI for the 3 holes, the higher noise, and we also see that these 3 holes have the same PCI value because they all arrive in phase at the same time. So let's try to explain why we have some high values of PCI sometime and low values. So when do we have a high value? We have a high value in the PCI image when a large portion of the emitter receivers sum exactly in phase. That means we are summing coherently. So like small reflectors like a SDH tends to send energy kind of everywhere. So it's going to be seen by all the receivers. So let's look at the pixel corresponding to this sideway hole right here. And let's calculate the time of flight for all the emitters receiver pairs. So for example, if we look at emitter 1, receiver 1, this is the phase signal that we have. For the time of flight, we obtain a minus 1, sorry. If we look for emitter 1, receiver 2, we obtain a minus 1, so same phase. Emitter 1, receiver 3, minus 1 again, so same phase, and so on. So if I display all the signals for emitter 1, that's what you have here, the 64 signals, this is like a B-scan, and I superimpose the time of flight to go from emitter 1 to the pixel right here, back to all the receivers. This is the red crosses that you see right here. And you can see that they are pretty much on the same phase for every single signals. So that means that they are all going to contribute in phase. I have a little animation right here. So now I look for every single emitter. So now you see all the receivers for every single emitter. And you can see that the cross stay pretty much on the same phase. So that means that every single signal in my FMC is going to contribute to the PCI image, and that's why I have a strong amplitude, a strong phase, sorry. So now let's look at the back wall. Why does the back wall and the front surface disappear? So let's look at the pixel right here. And same thing, we are going to look at, for emitter 1, at all the receivers. We fire emitter 1, we rebound off the back wall, and basically we detect on all the receivers. And this is the signal you see right here. And same thing, we calculate the time of flight to go from emitter 1 to the back wall and back to all the receivers. And this is what you have right here in red. And you can see that we only have this part of the B-scan where we actually have element in phase. Everything hereafter is actually not in phase. So they are going to basically contribute negatively to the PCI image. And if I do the same as before, if I look for every single emitters, you can see that my red crosses are not superimposed correctly. Here it's a little bit better in the middle when we reach element 30, 32. And then after, when we look at the emitters on the other side, this is the opposite. We see that we have signals are in phase right here and not in phase right here. So what's happening with geometry echoes, like the front surface or the back wall, is we only have mostly contributions from the symmetric path, so 1 to 64 and so on. All the other passes lead to incoherent sum, so that explains why we have low values for PCI. So we can kind of expect the same for other specular echoes, like a delamination, and sometimes maybe even some lack of fusions. What about the noise? I said that we have a higher noise for PCI. So when we are dealing with amplitude versus phase, the signal-to-noise ratio can be pretty high. Depends on the nature of the indication. If we have a back wall, a lack of fusion, we typically have a pretty strong echo. And the more energy we send into the part, the better the signal-to-noise ratio. If I crank up the voltage or if I crank up the analog gain, I typically have a better signal-to-noise ratio for my TFM image. Now, if we look at the phase, well, the phase always varies between -1 and +1 for the indication and also for the signal. So even if we send more energy into the part, we do have the same phase. It's still -1 and +1. We don't increase the value. So let's consider that we have a Gaussian noise with a zero mean, which is a typical electric noise. The more emitter-receiver pairs we are using to calculate our PCI image, the higher the signal-to-noise ratio. So typically, when you use PCI, it is recommended to use a greater number of sources. So for example, like a full FMC rather than a sparse FMC. And we will look at some example after. And with PCI, one advantage is we can theoretically predict the signal-to-noise ratio because we know that each signal is going to be either a -1 or a +1. So each emitter-receiver pair is going to contribute -1 or +1. We're going to sum all of them for all the sources and the receivers. And this can be described as a binomial distribution with equal probability of -1 or 1. It's 50% chance of either one. So if we look at a PCI image with 500,000 pixels, we take like a lot of pixels, and we look at the distribution of noise for full matrix capture and for sparse matrix capture, firing only 16 times, so every 4 signals. And we calculate the binomial distribution. And what you can see here is, of course, the noise is centered around 0, because we sum -1 and +1. So overall, this is going to be around 0. But you can see with the full matrix capture that there is not much noise after 6% or -6%. So that's kind of the level of noise you can expect when you use a 64-element probe with a full FMC. If we look at the sparse FMC, now we only have 1,024 signals, so 4 times less. You can see that the noise level can go pretty much all the way to 11 or 12%. So we're going to have a higher noise when we are using a sparse FMC compared to a full FMC. And what I did is I actually put my probe on a mockup. I try to be outside of any indications. I did a FMC and a sparse FMC. And if you look at the echo dynamic here, you can pretty much see that the highest noise is around 7% here. So close to the theoretical level. And if we compare with the sparse FMC, we are around like 12, maybe 13% here. So this is very close to the theoretical level. So that means that a user, an operator, can actually set the lower threshold of his dynamic range. So here I could set it to 12% because I actually know the noise level of my PCI image. So now let's look at some inspection, so mirror inspection, and I'm going to start with L0. And here it's pretty simple. I just have a plate with a notch at the bottom, and I compare again TFM with PCI. Something that we see very often when we do L0 inspection is those artifacts right here. They are called also isochrones. And those artifacts are coming from contribution from the back wall. If you look at the pixel right here, and we calculate all the time of flight to extract the amplitude of the pixel, for some of those time of flights, we're going to get some contribution of the back wall. So this is physical. There is nothing we can do about it. They are here. When we do PCI, well, they disappear. And the main reason is because PCI removes the contribution from the back wall and from the front surface. So it removes the contribution from the artifact. So we can actually detect our notch, the tip of our notch pretty nicely, and we can size it pretty nicely. For the TFM, if we had a smaller defect right here, maybe we wouldn't be able to detect the defect. So PCI is very efficient at seeing defect close to the back wall. So here I have 3 standard holes, although here we see them very well with TFM. I can see them very well here with PCI. I pretty much don't have any back wall anymore. Now I take my mockup and I flip it, and my holes are right here. I kind of see this one very well with TFM. This one, I kind of need to move it dynamically to see it, and this one, I actually don't see it. And with PCI, because we remove the front surface, I would expect to see the defects pretty nicely. And actually, this one, we can kind of see it, and those, it is kind of hard to see them. And this is kind of counterintuitive because the front surface is gone. What's happening here is from this defect, for example, the element 1 and 64 are really far. It is pretty much impossible for the energy to kind of go this way. So we don't have anything coming in phase. And that's why we don't actually see any defect very close to the surface. So let's look at hydrogen, high temperature hydrogen attack. This is a perfect application for PCI. So we have a mock-up, and you can see here a cross-section, stage 2. The cracks are ranging from a few microns to 100 micron. Actually, most of them are like around 50 here. We developed like a special probe for HTHA. This is a 64-element, 10 meg, and there is a focus in the passive plane to improve sensitivity in the passive plane because those cracks are small in both directions. And here you have a beam field calculation in the passive plane, and you can see that between 4 millimeter and about 30 millimeter, the beam field stays within smaller than 3 millimeters. And so again, I did an acquisition with Capture, TFM, and PCI at the same time. Forgot to mention that I'm using Capture and the Gecko here. We have it on a special version in real-time multi-group. We kind of see the artifact, the isochrones for TFM, and we don't see any defect at all because the energy of those defects it's really weak. For PCI, basically the front surface is gone, back wall pretty much gone, the artifacts are gone, and we can kind of see here the information coming from the HTHA. We have about 7 dB higher than the grain noise. If we look on the C-scan, so on the C-scan, I removed the front surface and the back wall. It kind of changed my gate. We see all the HTHA right here. You can kind of see the cloud of pixels. In this area, we don't have HTHA. You can kind of really see it here. On TFM, unfortunately, we don't see anything. So really, HTHA with the L0 wedge is perfect application for PCI. One of the problems of PCI is we have to use a full matrix capture to have a higher signal-to-noise ratio. So scanning speed can be an issue depending on the system. So we try to see if plane wave imaging could help because plane wave imaging is using less angles, so we should be able to go faster. So here we looked at 16 angles. In theory, if I use plane wave imaging with PCI, I should have more noise because I'm using 4 times less sources. But if we look here at the C-scan, it seems that we are getting pretty much the same result as before. So why is that? Why don't we have a higher noise? And this is compensated by the fact that if we look before, some of the FMC signals didn't have enough energy to extract a phase because the defects are so small that the signal-to-noise ratio of some of this FMC data is pretty much 0. So 0 means 0 amplitude extraction, but also 0 phase. By sending more energy with plane wave imaging, we have a little bit more energy on all the signals of the plane wave imaging matrix, so we are able to extract a phase. So this is how we can compensate for the noisier image due to plane wave imaging. And here in that case, because we are only using 16 emissions, we are going 4 times faster. So what about corrosion mapping, since we are looking at L0 inspection? You have here TFM, front surface, and you can see here the back wall. Well, the problem with PCI, it removes front surface and back wall. We don't see any front surface echo, so we don't have any reference to measure the depth equals 0. Can kind of see something here on the back wall, but really like PCI is not the best technique for corrosion mapping. I would stick to PAUT or TFM if you want to use TFM. And for the same reason, this is probably not a good technique for composite inspection. So here I have a carbon fiber sample, front surface, back wall. This is a flat bottom hole. I believe this is 3 or 5 millimeters, I forgot. And we can actually see also with TFM the plies. If we look at PCI, everything is pretty much gone. Maybe those are the plies, but we don't see the flat bottom hole. So PCI is definitively not a good candidate for composite inspection. So now let's look at some angle beam inspections and obviously mostly well inspection. To do that, I'm going to look at this sample here. This is a pipe we have at Eddyfi that pretty much has every single type of defect you can find in the world. So this is carbon fiber, carbon steel. For the inspection, I used a link scanner from our colleagues at Silverwing and 2 64-element probes in a multi-group configuration. So thank you, Olivier, for doing the experiment. For For TFM, we usually do TCG before, and we tried a lot of things. We tried full FMC, sparse FMC, and plane wave imaging. I will only show a couple of results, but if you want to see more results, you can always send me an email, and we can always discuss. The way I'm going to display the results, I'm going to look at the PCI on both sides. So 2 probes. I'm going to start with a full FMC acquisition. And the acquisition speed for 2 PCI with 2 full FMC is about 17 millimeters per second. So it's not super fast, but this is achievable. Here we have the 2 C-scan, and we can see a lot of contributions coming from the different indications. So let's look at them. And let's start with the lack of penetration and the porosities. Those are the easiest. The lack of penetration is seen from both sides, not a real problem. We also see the porosities here on the 2 sides, although it seems to be a little weak. So what we can do is we can actually change the dynamic range. If you remember, I told you that we can actually predict the noise level. So here, since we are using FMC, I'm going to set my lower threshold to 6%. This is the theoretical noise level. For the highest, I'm taking 5 times. This is a little bit more empirical. You will have to play a little bit with it depending on your sample. But the porosities are becoming more visible. This is purely visual. But we actually do have a pretty good signal-to-noise ratio on PCI here for the porosities, with about 19 dB, because porosities are volumetric defects, so they are perfect candidate for PCI. Root crack and toe crack, again, from both sides. So here we see the root crack from the probe opposite to the bevel on the same side, toe crack on the same side as the probe, and toe crack from the other side. So what I did is, again, I adjusted my dynamic range to between 6 and 30%, and obviously the tip diffractions are popping up on the, and we can then, after size, between the position of the corner echo and the biggest distance for the tip diffraction, we can do that from both sides. So here we obtain depths of 4 millimeters on one side, about 3 on the other side, so a little bit of a discrepancy here. And for the root crack, toe crack, same thing, tip diffraction, corner echo, tip diffraction. Again, a little bit of a discrepancy here. This is probably due to the fact that we rebound off the back wall, so we might be perturbed by the root of the weld. But that kind of shows that you know, like any weld inspection, you pretty much have to do inspection from both sides. I think it would be really hard to size every single defect from only one side. Lack of fusion and sidewall crack. So here, the lack of fusion located on the bevel, same side as the probe, so bouncing here. The same defect detected by bouncing off the back wall on opposite side of the bevel. I can kind of see some tip diffraction. Same thing here for the sidewall crack. So here we see on the bevel opposite to the probe, and same side. So again, I'm going to adjust my dynamic range between 6 and 30%. All the tips are becoming more evident. I'm positioning my cursors on the maxima. So one here, it's hard to tell, but the maxima is actually right here. We can measure the altitude, the depth, 4.9 millimeter. We can do that from the other side, 5.6. So again, bouncing this way. The sidewall crack, one tip diffraction here, one tip diffraction here, and same thing here on the maxima. Actually, there is one right here and one right here. So 6.2 millimeters, 5.3. So pretty close. Still a little bit of a discrepancy when we do the measurement from both sides. But again, that's probably due to the fact that when we do on the opposite side, we bounce a little bit off the root. So it looks like PCI is actually pretty good at detecting the tip diffraction. So that would help for sizing for any cracks or lack of fusion. However, I would like to have a couple of warnings. I looked at another lack of fusion on another mockup. And again, I did TFM, I did PCI. The TFM basically will show a very strong specular echo. I'm using a decibel drop to try to size the defect, -6 dB. And I would expect PCI to show 2 tip diffractions. Unfortunately, it's only showing 1 echo right here. And if I only have 1 echo, because it's a non-amplitude-based technique, I can actually not use a decibel drop, and I cannot size my defect if I only have this. So if I only use PCI and I had this response, I wouldn't be able to size my defect. So I probably would have to change my index offset and or look from the probe on the other side. So if you only use one PCI and you end up having a result like this, that means that you will have to do something to be able to have 2 tip diffractions. And so here is a zoom. Again, I changed the dynamic range from 6 to 30%. Maybe there is a beginning of a tip right here, although it doesn't seem to be on the same depth. But here I don't have a tip on the other side, so I cannot really size. So if I try to explain why sometimes we can only have only 1 echo instead of 2 tip, so if I look at the angles, so again, that was a FMC, that was not a plane wave imaging, but I'm going to use that and I'm going to look at the angles for explanation. If I look at the position of my defect, the middle of my defect is located perfectly for my 0 degree. So it is well centered with respect to the 60-degree refracted angle. So what's happening here, this is very similar to the back wall. Remember, at the back wall, we had something in the middle of the back wall, we had some energy that were coming from the contribution, the symmetry contribution. And this is exactly the same here. Because the defect is centered with respect to the refracted angle, the natural refracted angle, we have some signals that contribute in phase, and we have a signal here instead of having 2. So fortunately for us, a lot of the natural defects are going to have some roughness. Hopefully, this is kind of a rare example, and we should have some kind of tip diffraction pretty much all over the place to be able to size properly. A second warning regarding positioning of tips. We can, with a PCI, we can size on the first leg, on the second leg, or some people also can use the third leg if they want to. So here I have the same lack of fusion as before, but I put my probe against the well cap. And here we can see that we have 2 tip diffractions on the second leg. I can position some cursors, and I can measure the height of my lack of fusion, 3.9 millimeters. If I change my dynamic range again, kind of crank it up, I can see that I also have tip diffraction on the first leg. So I guess I can do the same, right? I can position my cursors on the maxima, but here I obtain 5 millimeter. If I go back here, I have 3.9 and 5 millimeter. So you can kind of see that the position right here on the first leg is not the same as the maxima right here. So I think we need to investigate a little bit more why we have this, but keep in mind this as well. If you do first leg and versus second leg sizing, you might have some differences. All right, now going back to plane wave imaging. As I mentioned before, scanning speed is about 17 millimeters per second when we do 2 full FMC. And I forgot to mention we have about 100,000 pixels on each of them. So that has a huge impact on productivity, and it could be difficult to scan at 15, 17 millimeters per second. So we have implemented plane wave imaging in the past to improve scanning speed for TFM. By firing less times, we can go faster. The problem with plane wave imaging and PCI, it depends on the number of excitations. So the less angles I use, the more noise I'm going to have, and potentially I'm not going to be able to distinguish my tip diffractions. So to evaluate that, we did an inspection with 4 groups, which is the maximum you can have in capture, 2 TFM and 2 PCI, 8 angles per group, and 100,000 pixels per group. So here we are looking at 1 TFM on each side, 1 PCI on each side, 8 angles, you can see them right here, and 100,000 pixels per group. So the scanning speed is around 38 millimeters per second for the 4 groups. So we can imagine that if we are switching only to 2 groups for PCI with plane wave imaging, we would be above 70 millimeters per second, which should be a good speed for scanning of wells. So if we compare a full matrix capture to plane wave imaging, with only 8 angles, we can theoretically predict the noise, and it should be around 16-17% maximum. So if we look at the lack of fusion we had before, we can evaluate the signal-to-noise ratio on the full matrix capture, which is about 22 dB for the full FMC. And here on plane wave imaging with only 8 angles, it goes down to 12 dB. So that's a pretty dramatic drop, like about 10 dB. But 12 dB is still sufficient to do some sizing. And we can actually see for that position, we do still have tip diffractions here for sizing. So we think like if you find the right amount of angles, you should be able to use plane wave imaging with PCI. And if we quickly look at all the other defects, so I adjusted my dynamic range to 16 for the lower threshold because that's my noise level. I went to 50%. Again, that's kind of empirical. And all the defects are detectable. So here is your toe crack, corner echo, and tip diffraction. This is the sidewall crack from same side as the probe with on the second leg, and you can see also tip diffraction on the first leg. Those are the porosities. This is the toe crack with some tip here. So here we didn't miss any defects. We need to do a little bit more evaluation, more investigation with plane wave imaging to see if 8 angles is sufficient in all cases. But we can always use a little bit more and drop a little bit in scanning speed. It's kind of a compromise you have to find. All right. Before conclusion, I just want to show like a live image. I'm just gonna. So here, this is a configuration. I have TFM on the left using full matrix capture, PCI on the right. This is the lack of fusion with my tip diffraction here. You could obviously switch, your color palette. This is, you see the color palette from one of our competitors. It's available. You'll be able to use it if you prefer this one. As I mentioned before, you can kind of use this one. You can adjust the dynamic range to be able to see the tip diffraction. So here, I think I have a toe crack right here on, you can see it on the first leg, second leg, sorry, a little bit on the first leg. If you remember, like PCI is not really good close to the surface. And I believe I have my toe crack right here. So toe crack, again, the dynamic range has been changed to 30%. That's why I have very strong amplitude compared to the TFM right here. But here you go. This will be available in the next version of capture. So in conclusion, PCI is a complementary technique that provides good sizing capabilities by looking at the phase coherence between the different signals of the FMC. It is compatible with any acquisition scheme, so the FMC, spares, plane wave imaging, and if your system allows to do virtual sources or stuff like that, there shouldn't be a problem to do PCI as well. So PCI removes geometry echoes, like front surface, backwall, and any artifact linked to those surfaces, like the isochrons, when performing laser inspection. So this is great when you are looking at a defect close to the backwall. It provides tip diffraction echoes from crack better than TFM because you don't need to calibrate with the TCG. So it is better for sizing. However, we saw some discrepancies when sizing from both sides of the weld on the first and second leg, and also from both sides. So a little bit more investigation is necessary on our part, but that means that it is probably necessary to do a PCI inspection from both sides of the weld. I don't believe that one side will be sufficient for sizing cracks and lack of fusion properly. As I mentioned, it will be available in Capture 4.1 as a multi-group technique for the gecko and the mantis. So what are the pros? I think PCI is a good technique for sizing for lack of fusions and any cracks because it provides the tip diffraction echoes better, and you usually have about the same amplitude from the top and the bottom. Not always, but you tend to have kind of the same amplitude, same value, not amplitude, sorry. Usually you have better visualization of volumetric defects, like porosities or slags, because they send energy everywhere. This is really good for PCI, so you don't have to increase the gain in analysis. Obviously, they are visible in TFM, you just add some soft gain in analysis, but here you can see them very well. I forgot to mention, but it's also less sensitive to orientation. So typically when you have your weld axis and your probe, you try to be normal as possible. If you have some tilt like this, especially for planar defect, you're going to have a drop in amplitude. Well, with PCI, if you have a slight tilt, as long as you get a signal, well, you can extract a phase. So PCI is a little bit less sensitive to the two probes orientation. As it removes artifacts, this is a great candidate for the detection of small defects on the L0 inspection. So HTHA will be a great candidate for PCI. And because you don't need to do a TCG, it doesn't require calibration if you want to use tip diffraction measurements. The disadvantages. The signal-to-noise ratio depends on the number of emitter-receiver pairs. So usually it is better to have more sources. However, more sources means a drop in scanning speed, especially if you need to do inspection from both sides. Obviously, you can do one side first and another side after, but you double the amount of time for inspection. We saw that plane wave imaging might be a solution to that, but to the detriment of signal-to-noise ratio. So you have to find the right amount of angles to obtain sufficient signal-to-noise ratio. It is possible for some smooth defect, like we just found a lack of fusion, not to display any tip diffraction. And because this is not an amplitude-based technique, if you only have one echo, you cannot size the defect, so you kind of need to rescan your sample, changing your index offset, and or look from the group on the other side if you have two groups. As it removes geometry echoes, obviously this is not a good candidate for corrosion mapping or composite inspection. Even for hydrogen-induced cracking, for the delamination, that might not be the best candidate to look for these delaminations. Of course, it would be great to find the connections. So maybe if you do HIC, you combine TFM to find the delamination and PCI to find the connection. Although I believe that TFM is sufficient for HIC. And also defects close to the front surface are not detected very well. This is counterintuitive because the front surface is gone, but I wouldn't use PCI to look close to the front surface. All right, thank you very much. Sorry, I mean, it was a little bit longer today, and thank you for staying with me. All right, so now we can look for questions if we have any questions. Up to which thickness PCI will work? Well, essentially the same as TFM. I know it's a kind of a weird answer, but you can use it for 100 millimeter to 100 millimeters. Of course, you need to use the right probe. Your aperture for your probe needs to be large enough to be able to focus the energy in the near field. But I don't believe that there is a limit with PCI. Kind of the same as TFM. Depends on your aperture and your central frequency. Can PCI replace TFM to inspect wells? I think it's a little bit too early to use PCI only to inspect wells. I think ideally it would be good to be able to combine TFM and PCI at the same time because TFM would be able to obtain strong specular echoes and you would be able to size using a decibel drop. And you can confirm with PCI if you are able to obtain tip diffraction. So I think it's a little bit early for PCI to replace TFM. We'll see in the future. Is there a possibility to combine TFM and PCI? Yes, this is called PCF for Phase Coherence Factor. And this is already available in Ultravision. Our colleagues at ZTech as a post-processing technique. So PCF is the product of the TFM image with the PCI image, and you apply some kind of coefficient to the PCI. So obviously you need to calculate both and then multiply them, do a kind of a fusion of the two images. The advantage here is your noise level will decrease a lot because anywhere you have a very low noise, the TFM has no information, so you will decrease the noise of the PCI image. And when you have lack of fusion, you will have a specular echo on the TFM, tip diffraction on PCI. The product will only keep the tip diffraction. So it's a possibility, and obviously that's something we are looking at. But this is already available with UltraVision. Okay, PCI is powerful technique. How can we size small defects? Porosity is 3 millimeter of lens. So that's one thing is when your defect only provides one echo because it's phase-based and not amplitude-based, you cannot really calibrate PCI. So let's say you have 0.5 millimeter porosity and you have a 1 millimeter porosity, they are probably going to provide you with the same response on PCI. So on TFM, because there will be different sizes, you will have different amplitude. So with calibration, you will be able to kind of estimate the size. With PCI, for very small defects, I don't believe that you will be able to distinguish between two small porosities or two small side holes. You need to be able to have enough length of the defect to have two tip diffraction to be able to size it. Okay, so the difference between PCI and SCF for sign coherence factor. So if you go back to the list of publications that I gave at the beginning, especially with Camacho, kind of did some study on the difference between the full phase and the sign, and pretty much there is not much difference. So that's why people tend to use SCF for the implementation on hardware. Our colleagues, not colleagues, but our competitor is using the same thing because calculating SCF is a lot easier on a FPGA compared to calculating the Hilbert transform. So to be honest, just go look at the publication. There's not a big difference. It's small, but it's not a big difference. Is PCI going to be available on the Topaz line? Yes, of course. We don't want any jealousy between us and ZTech. We are all friends now. So PCI will also be available next year in UV Touch. So for those of you who prefer the Topaz and the UV Touch products, you will also have access to the same PCI. So capture 4.1 first quarter of next year for Mantis and Gecko, and probably just a little bit after for Topaz. But both lines will have the technique. Can PCI remove the need for scan multiple index points? To a certain extent, yes. I will tend to put the probe close to the well cap. Usually, when we do TFM or phased array, we tend to position the probe to be normal on the second leg to have a pretty nice specular echo. To favorize tip diffraction, I will tend to get closer. So I will say, like, yeah, you probably don't have to do multiple index points, especially if you do inspection from both sides. If you have a lack of fusion on the side opposite to the wells on the first leg, you could have the same problem I've shown. You could only have one echo potentially, but if you do inspection from the other side, you will have two tip diffraction. So yes, I think that's a good point. You probably don't need to have multiple index points. Is PCI will provide a better performance in thin material instead of traditional PAUT? For L0 inspection, definitively not. As I showed before, if you have any defect close to the surface, PCI will have a hard time to find them. For traditional PAUT, if you do a linear scan, because you only look at L0 inspection, as long as you are not in the dead zone, you should be able to detect. So I would say like PCI is probably not better at thin materials for L0. As far as angle beam, so for example, let's say we have thin boiler tubes, I would say this is probably the same as thicker. I don't think it's any better, although we have to try. We haven't tried, to be honest, on very thin stuff for weld inspection. Okay, Philippe. Yeah, TFM and Tula on HTH chain, no, it's like only PCI works. Well, I think it's just part of the evolution of technology. I think Tula is great because it's pretty fast. It's low angle, Toft probes. TFM basically is a little bit slower. And now if you go to PCI and you need to do a a full matrix capture, you will be limited in terms of scanning speed. So I think it's just a natural evolution. I hope Lavender introduces PCI in their course, and they have a lot of samples to evaluate. So for me, it's just like, as I said, PCI for me is not here to replace anything before. This is just like another tool. We have conventional UT, we have TOFT, we have phased array, we have TFM, and now we have PCI. I don't believe PCI is going to replace everything. How fast is PCI compared with TFM and PUT? So if you do a full matrix capture, PCI has the same speed as a full matrix capture for TFM. So for example, if you use a 64-element probe and I don't know, 100,000 pixels, one group on the gecko, don't quote me on that, but you are probably in the 30 millimeters per second range. You see PUT would be much faster. If now you can use plane wave imaging instead of FMC, and again, be careful because the noise is going to increase, then you're just going to reach like 70, 100 millimeters per second. You really have to evaluate on your sample if plane wave imaging is usable. Okay, I wish I had the answer to this one. In theory, yes. If you look at publication, PCI seems to be providing better results for austenitic materials. I personally have not used that yet. That's kind of the next step I wish I had for this presentation today. But some results from some customers with the gecko and the PCI had tried, and according to them, they have some better results. So hopefully in the near future, we'll be able to test and put on LinkedIn and other social media some results. But apparently, according to publications, that's the case. Salut Frederic, another Fred. So we talked about error on positioning. So I try to show that today on the first leg and the second leg, and I think the problem here is I need to find a sample like an EDM notch that doesn't have like one of my posts on LinkedIn. I put a PCI on EDM notch, but it has a very small hole, so it's not really usable. It's more the difference between the first leg and the second leg. You tend to see that the tip diffractions are not necessarily positioned exactly the same way, and your height measurements on your lack of fusion is not exactly the same. So I still need to investigate that. It's not a major difference. It's about 1 millimeter, but 1 millimeter can be kind of big on a 4 or 5 millimeter defect. So definitely don't want to undersize it. So I need to find the right samples for that. The right samples and the right defect. But it became like a more. I like PCI now more than when I met you. For PCI, does it require a specific probe? No, this is kind of the same probe as you will be using for TFM or for phased array. Nothing in particular. And actually, if you look at the first publication in my presentation, you can go back after. The Camacho is actually using PCI in phased array to remove grating lobes. So I don't think PCI actually doesn't require any specific probes. It can be used with any probes. That's kind of the same question as before in austenitic steel, stainless steel. According to literature, yes, you will get good results with PCI. Unfortunately, myself, I haven't tried yet. And some customers who had the luck to use the gecko and this PCI version, again, had some interesting results. So I hope we will be able to communicate soon. So here is my email address again, freverdy@eddyfi.com. If you have any questions, or if you want to organize a meeting to see more results, and please, you can post on all the social media comments, and I will try to answer as much as possible on your comments I was not able to answer today. So again, thanks for staying with me today. It was a long coffee break, and I hope you enjoyed it, and see you next time. Enjoy the end of the year, and great holiday season. All right, take care.